We are looking into transverse deflection of beams. The word transverse here has a lot of meaning. We are not looking into axial. So when you have a beam, if you draw a three-dimensional beam, your longer dimension is, of course, your length of the beam, right? And there can be support here. Sorry. So this is my longitudinal axis, right? And that axis is X. Okay. And this is my vertical axis or transverse axis, which is called Y. There is another transverse axis, which is Z, right? Now we said that our load is only along this axis here, acting like this, right? So load is acting along Y direction, and therefore if it's symmetric about Y axis, then it has to have deflection also along Y axis. So that is called transverse deflection. So the beam will bend like this. Okay. Note when we do transverse deflection analysis, we don't look at every point of the beam. So from 3D picture, you get a 2D picture of the beam, right? Because Z is immaterial to us right now. This is my X, neutral axis, and that's my Y. For deflections, we only look at this line, the neutral axis, and this is called elastic line. We look at the deflection of this line. Okay, so sometimes they call it elastic line diagrams. Elastic line diagram meaning diagram of the deformation of the elastic line. Okay, we don't completely draw the full beam and show its deformation, because the deformation in the top layers and the bottom layers will not be same as the neutral axis layer, because they will have compression and tension, and this compression and tension will increase their length or decrease their length, whereas neutral axis will remain same as length, same in length, and therefore we look at the deformation of the neutral axis only, right? So that's the important thing that you need to know. What is in syllabus is force deformation relationship. That is what we're going to learn today. And then how to find deformations through various methods, right? Integration method is one of them. Using singularity functions or discontinuous function, or we call it Macula's bracket, that's another one. Next is I will teach you moment area method and Castigliano's theorem. Before Castigliano's, we need to learn strain energies. These two are very interesting methods, okay, and they're important if you want to find solutions at a particular location of the beam, not the complete beam. Okay, so quick checks, and they're very quick solutions. They're useful for certain kind of beams, which we will also discuss. And if you get those beams in your, in your practice, you use these two methods, moment area or Castigliano. Then we learned about superposition methods, which is based on Maxwell-Betty's law. Maxwell-Betty's law is not part of the syllabus, but you can read it in the books. It's a very good, thing to understand, and it has a very nice proof. Okay, and that proof is illuminating in the sense that will give you nice ideas about how beam deforms, how beam behaves, how strain energies in beams are calculated, right? So all those things you will get idea if you go through Maxwell-Betty's law and its proof. And it will also help you for people who are looking for higher studies, in the sense finite element higher subjects like finite element methods, and then solid mechanics. It will be very good for them to go through this. It is a very nice proof, right? And finally, we will end it with strain energy in bending, which will help us to find Castigliano's theorem. Okay, so let's get back to our job, deflection in beams. Now, when I said deflection, I always said that we are looking into transverse deflection of beam. So if you have a beam, I'm drawing it like this, and then I have a load here. Let's say P load is acting. Then the beam will deflect like this, right? This is called deflected set. And if this value is V, then V is, of course, is a function of x, right? Because you can see the v is different at different location. It is 0 here because of the boundary condition. Let us consider a cantilever beam. So it is 0 here because of the boundary condition, and it is maximum here at the free end. So therefore, it's a function of the length x, the position x. Okay. And also we know that the slope of the beam is here, right? This is the slope of the beam, the angle that is made, and that slope is changing, and the slope will be theta, will also be a function of the position x, because slope here at the fixed end is 0, and as you can see, the slope is going and maximum somewhere here. Okay, slope theta we have to find out. One thing we have to do is to find a relationship between v and theta, and then find relationship between theta and the load that is coming onto the structure, that is bending moment and shear force, capital V, and shear force. And then finally we have to relate moment and capital V with the load that is acting on the structures. Either it will be omega or the P load that is there. So our job is to relate them today, and that relationship is called fourth order governing differential equation. Okay, so fourth order in the sense the relationship will have a fourth order differential equation in deflections, and that relationship is what we are going to find today. Okay, so first thing is we are looking only at the elastic line. Second thing is we are looking only at the transverse deflection. We are also telling beam is homogeneous and other things are already there, which will come as we go on. The assumptions will keep on coming, right? And few more assumptions we'll do. Now what we know a few small things. One of them is we know the curvature, right? A curvature kappa is given as 1 by radius rho. The radius is radius of this point from some origin 0. So radius of the curvature, right? Radius of the curve that it forms on my rho. And we also found out from our previous relationship, if you go to the next slide. So it is a cantilever beam here. Okay, so this is a cantilever beam. This is a point where it is fixed at a point, and this is my elastic line AB. So AB deforms because of the load P acting here, it deforms like this, it goes up. Okay. And this distance is known as the transverse deformation. This is V, which is called transverse deformation. And obviously V is function of the position X. We know there is a flexure formula. The flexure formula is, our starting point is always a flexure formula, and the flexure formula is given here. As you can see, the flexure formula is M by I is equal to E by rho is equal to sigma B by Y. I hope you remember this formula. It comes from two formulas. One of them is sigma B, that means bending stress is My by I. So you can see this relationship, this and this. Okay. The second relationship is sigma B equal to kappa E Y. This relationship also we have found out. Before we found My by I, right? So these two relationship, so this relationship will also give this two relation, right? Remember that kappa is equal to 1 by rho. So the third relation that is going to be used is kappa equal to 1 by. Okay. If you use this relationship, you get the flexure formula. Okay. Now look at this cantilever beam that we have. It is fixed here, and the deformation has to, it has to abide by the boundary conditions. Deformations cannot go beyond boundary conditions. It has to always satisfy boundary conditions. Okay, never ever make a mistake. Deformations and slopes, these are geometric characteristics of the beam, and they definitely have to support the boundary conditions that are there in the beam. So the boundary condition at this point is, it is a cantilever beam, and therefore the beam cannot go up or down. So there is no deflection here. It's a zero deflection. Similarly, it's a fixed thing. So there will be slope also will be 0 because it cannot rotate about this point here. So both theta and V has to be 0 here. right? But it is not to be 0 at anywhere else if there is a load acting. So the beam, let's say it was initially like this, it has now bent like this because of the load that is given here, P. Now, if you take 2 points, M1 and M2, okay, M1 has a deformation of V, M2 will have a deformation a little bit more than that. If it is dx distance away, then it will be V plus dV, okay. So M2 has a deformation, location M2 has a deformation V plus dV. And the angle that is subtended by this ds is called d theta, okay. Therefore, you have already found out that rho, d theta and ds are related. We have used it earlier, and the relationship is 1 by rho is ds by d theta by ds. Sorry, it will be rho d theta equal to ds, right? So if I use them, so v is my transverse deflection along y-axis. Theta is the rotation about z at any point in the beam, or called slope. It's called slope, an angle of inclination theta x. Okay, so how do you calculate theta? Theta will be, let's say at this point you are calculating theta, so you'll put a tangent at this point, and then this is your theta of x. Okay, and as I said, we know this relationship, rho d theta is equal to ds, and therefore d theta by ds is equal to 1 by rho, which is my curvature. So kappa is going to be d theta by ds. So I got one formula already, that kappa is equal to d theta by ds. Okay, now look at here, look at this picture here. We have taken only a small portion of this, and this small portion is drawn here in an elaborated fashion. So this is my M1 point, this is my M2 point, and this is my V deflection at x, right? And this is my V plus dV deflection at x plus dx, okay? And this length is dx. Now, if I draw this triangle, join M1 and M2, because they are very near, they will go along the curve because they are very near. I'm looking at very small dx, right? Infinitesimal small. So this is my small triangle that I have, and if I draw the triangle here, I have here dx, I have here theta of s, I have here dv, not theta of s, this is d theta of s. Okay, no, this is theta, right? This is my theta, and this is theta plus d theta. Yeah. So my tan theta is going to be dv by dx. Okay. So tan theta is going to be dv by dx. For a small change in v, we are doing all those things. So we are looking at linear. So my first assumption here, okay, that assumption will come here. First assumption here is deflections and slope are small and within elastic limit that means they keep the beam linear. Okay, all right. So if I assume theta to be small, I have tan theta is nearly equal to theta, so dv by dx is nearly equal to theta, right? But remember this formula, don't forget this, will come back to this. Similarly, cos theta is going to be dx by ds and sin theta is going to be dv by ds, right? You can find that from this relationship. This is ds, this is dx, and this is your dv. For a small deformation, we'll assume ds is equal to dx. And if I do that, then my kappa is becoming d theta by dx. And if kappa is d theta by dx, and I know theta is dv by dx, so I can replace that. So it is ddx by dv by dx, and that gives me kappa as d square v by dx square. Remember, I have made an assumption of linear. Okay. So curvature deformation relation in linear, within linear zone, okay, that's written here. Okay, a is given by d square v by dx square. So take a second derivative of deformation, transverse deformation with respect to the x-axis. Okay, all right. Now that's one relationship we have found. We have to find another relationship, how it relates with moment, right? But remember that moment and kappa are related through the flexure formula. This is my flexure formula, and moment, that is this, and kappa, that is 1 by rho, are related. And now kappa and deformation are related from this formula. Therefore, I can always relate moment with deformation. And once I know moment, bending moment with deformation, I'm actually relating load with deformation. Okay, so that comes from this relationship. So m of x, that means moment at any location x, is going to be equal to ei by x. So ei, that is called flexible rigidity at that location x, into d square v by dx square. This is called moment deformation relationship, and ei is called flexible rigidity. I think we have talked about this before. I'll write it here also. ei is called flexible rigidity. Okay, it actually defines how much deformations the beam will have for a unit load. So that's its definition. There are a few sign conventions that we have to worry about. This is my positive moment. This is a sagging moment, positive. This is the shear force, that how it's going to be positive, and this is how the load is going to be positive. So downward load is considered to be positive. Now, once you know moment relationship, you can always find relationship with the shear force. We know this relationship. We have learned it in the last year engineering mechanics course, that dv by dx is equal to minus q and dm by dx is equal to v, right? So it comes out to be d square m by dx square is equal to minus q. Q is the distributed load on the beam, not a point load. It's a distributed load. And we can relate this. So m can be replaced with ei d square v by dx square. Once you do that, you get the relations here. So v is ddx of ei d square v by dx square, and minus q is d square by dx square ei d square v by dx square. Okay, this is called fourth order differential equation, and this is my governing equation of statics for a beam deformation. Okay, all right. So if I write those equations, so for with shear force it is a cubic order, and with load it is third order, with moment it is second order, with slope it is first order. So remember those relationships. Okay, remember that if ei is constant, I can bring it inside, but if ei is not constant, I cannot bring it inside. So it's customary to write it like this. Okay, once ei is constant, you can write next line ei is constant, and then you can bring it outside and write this d4 v by dx4. That you can do is equal to minus q. A few important points about the differential equation. So this is my governing differential equation. It's called fourth order governing differential equation of beams in statics, okay, not in dynamics. So not in motion. It's a static equation. It's a fourth order differential equation. Therefore, it will need 4 boundary conditions to properly solve it, right? What can be its 4 boundary conditions? It can be 4 deflection boundary conditions. It can be deflection and moment deflection and slope boundary conditions. It can be deflection and moment boundary conditions. It can be deflection and shear force boundary conditions. But there should be 4 boundary conditions that are necessary to solve it. Okay. For a prismatic beam, 1 minute, constant coefficient, Q of X is distributed load. Remember this, don't forget this. This is very important. This is one of the constraint of this equation. The equation needs to be properly modified for a point load or moment load. We'll learn that, how to do it. The equation is valid for X between 0 and length of the beam. That's all I have here to say. And a few more things here. 1 minute. When you have ei constant, it becomes a fourth order differential equation, as you can see. And when ei is not constant, you get this. So these 4 equations is what you have to remember. The relationship between transverse deformation with slope, with moment, with shear force, and with load Q. Okay, and you have to put appropriate boundary conditions to solve these problems. Right. Solve 1 or 2 problems, and the rest I'll leave it to you to solve, because we are going to use the same integration methods everywhere, and just 1 or 2 examples would be enough. First example, we have a simply supported beam here. This is a simply supported beam, okay, of length L, and on the top of it there is UDL given of intensity Q Newton per meter. When I write per meter, meaning there is a width here, right? Right, and there is this length here. Okay, so what you are doing is you have a load, you are dividing the load in a line load. Okay, and then line load in the sense you have a load that is distributed over the area, right? when you call it pressure, it is distributed over the area. And then you calculate it so that you get a line load. When you say a line load, it will be distributed over the line, right? So it's going to be Newton per meter. And you have to understand the boundary conditions. We have talked about boundary conditions before also. So for a simply supported case, the boundary conditions are at A, what we have, x equal to 0. Let us start our x from this point. So this is my start of x at this point, and therefore I have at x equal to 0, v is equal to 0. That means transverse deformation is 0. What about slope? Slope is not 0, right? Because this is free to rotate. So slope is not going to be 0. What about moment? Yes, moment is going to be 0 because it's a simply supported beam. Similarly, on the other side, at B point, you get V of L to be equal to 0 as well as the slope to be equal to 0 at L. These are my 4 boundary conditions. I got my 4 boundary conditions. I know my 4th order differential equation. I can solve it now. Okay, so this is my 4th order differential equation. And it is a prismatic beam with same E, therefore it's a constant EI. Therefore, I can take that constant EI out. So it's going to be d square V by d4 V by dx4 equal to minus U. Just integrate it, you get something like this with a constant C1. Okay, this constant C1 is due to shear force. It is the boundary shear force. When you solve it, you will see that these are boundary shear force that will come out here. But we don't have any boundary condition from shear force, right? Therefore, we cannot write it there. We don't know those values. If you know those values, you can put it. Now integrated once more, we have EI d4 V by dx4, sorry, d square V by dx square, because I'm integrating once more. And then this is qx will become half qx square, C1 will become C1x, and plus there will be another constant coming, integration constant C2. Now you have 2 boundary conditions at this level, right? At the moment level, you have 2 boundary conditions, one at x equal to L, which is 0, one at x equal to 0, which is also 0. So I can put those 2 boundary conditions. So EI d4 V by dx square, d square V by dx square at x equal to 0 is equal to 0. That provides C2 equal to 0. And at x equal to L, it also again 0. And you can write the equations for x equal to L. That comes out to be C1 equal to half QL. Now, what is half QL? If Q is your unit load, then QL is the total load. Half QL is the shear force. The boundaries, right? Half QL. Okay. So now my equation of static has become EI d square V by dx square equal to half QX square plus half QLX, which can be written as half QX into minus X, just to make sure that it is easy to integrate. But note, this is nothing but the bending moment equation at any location X, right? If you remember, bending moment equation is this. So this is how the bending moment looks like. And the bending moment equation is half qx into L minus X. So we actually, if you know the bending moment, we actually can start from this relationship itself. There is no harm unless it is said that you start from 4th order differential equation. You can always find bending moment, and once you find bending moment, you can start from this relationship. And remember, bending moment are generally, mostly, it will be continuous. Discontinuity comes when there is a bending, when there is external moment acting, but for most of the cases you will find bending moment to be continuous. So this equation to be used is not going to harm your calculation. Integrating once more, we will get slope. So that comes out to be this, where C3 is the constant of integration, and you cannot find C3 because you don't have any slope boundary condition. Okay. Then if you integrate once more, you get the deflection. EIV is equal to this. And we can now use boundary conditions 1A and 2A. That means V at x equal to 0 is 0. V at x equal to L is also 0. So V at x equal to 0, 0 is C4 equal to 0 because that goes to 0. This is 0, this is 0, this is 0. So that goes to also 0. V at x equal to L, you write that expression and put it to 0, you will get C3. So C3 comes out to be minus QL cube by 24. Once you put that back into the expressions, you get V value, what is 1 by EI, and this big relationship. You see, this is a cubic order relationship. Sorry, 4th order relationship. So a beam deflects, a simply supported beam under UDL deflects to the 4th order of its axial or spatial coordinate X. So this is how V is given, and this is how Q is given. Theta is given. okay, for a given Q. Now you see the relationship: as you increase Q, your V increases. As you increase EI for the same Q, your V decreases. Okay, so V is inversely related to flexural rigidity. V is linearly related to Q. Similarly, theta also inversely related to rigidity or flexural rigidity, and theta is directly related to the load Q. And also note, V is positive upward in this case, and theta is positive anti-clockwise in this case. Okay. Now you're getting minus here, right? Minus here, right? So it is upward positive, so therefore the deflection is downward. Now you see slope and deflection. So this is my theta A, which you can find from here. At x equal to 0, your theta A is going to be, this is 0, this is 0, QL cube by 24 EI. So this is your theta A. It's symmetric, so it's going to be same on both sides. V is 0 here, V is 0 here, and your V diagram is going to follow a fourth order polynomial, so it's going to look like this. What is the maximum value? You can find the maximum value at dv by dx equal to 0, that means slope 0. So this is the point where you have maximum deflection. And that you can find out is going to be L by 2. And once you put L by 2, you get 5 by 384 QL4 by EI. See the value here, 5 by 384. It's very small. And this is your slope diagram. It's going to look like this. Slope is maximum here, and 0 at this point. And deflection is going to be minimum here, 0 here, 0 here, and maximum at the center point. Which now look at the deflection diagram. It's almost similar to your bending moment diagram, right? It's almost similar to your bending moment diagram, and this is how it's going to be for most of the cases. Okay, and here it is written how to find Vmax. You have to put theta is equal to 0. And once you put theta equal to 0, you get the location Lx is equal to L by 2. And then you put x equal to L by 2, your V expression, you get your maximum. A few things to note. V is max at the location where theta equal to 0. This is not, this is always the case, but remember that it cannot be always true. It's not true for cantilever beams, for example. Okay. For simply supported cases, you can assume it to be true. It is as true for simply supported case. It may not be true for overhang also. So you have to be a little bit careful and use it. V of x is function of x by L whole fourth, and theta of x is function of x by L whole cube. And as I said, V of x is proportional to Q. V of x is proportional to m of x. V of x is inversely proportional to EI. Okay? A few of the relationships which you have to remember. I'll stop here. If you have any question, I would be happy to answer. And for a cantilever beam, you have to do the same thing. Only thing that is the boundary condition will change. Remember, the boundary condition for a cantilever beam with the fixed end is going to be V equal to 0 and the slope is equal to 0. V dash is 0. And the free end, you have moment 0 and shear force 0. And you can find the solution. Okay. Now let's go and ask you a question. How are you going to solve a problem like this? Remember that we had Q as distributed load. Now you don't have a distributed load, you have a point load. How are you going to solve? Are we not going to solve? Well, there are other methods to solve, but we can use this method also. How are you going to use this method? We have to convert our P load to a distributed load. So right now I'm writing it as P is equal to P into Dirac delta of x minus A, where a Dirac delta function is making it to be a continuous over the full space, 0 to L. Okay, I know it's, its definition. This is the definition. Delta of x called Dirac delta function, which is given as d of delta of x minus A is equal to 1 for x equal to A, otherwise it is 0. So it's a continuous function. Now you can do its integration. Okay, if you know how to integrate Dirac delta function, you can do its integration. And once you do its integration, you will get moments, or you can start from moment itself. right? You know the bending moment diagram. Once you know the bending moment diagram, you can do this integration up to this point and then do integration up to that point separately, right? So you'll get the deflection something like this. Okay. So either you start from bending moment directly, because bending moment is known to you for a simple supported beam with a point load. Start with that and integrate twice to get your deflection, or you convert your P load to Q using direct delta function. Either of these you can use. Solve it and tell me where do you get its maximum deflection point. Is it under the load P, or is it at the center, or is it in between somewhere? Okay, just solve it and tell me what happens when you have a point load at any point A. Now also, those who are interested in coding, can you please code and see what happens when P moves? Right, you can draw a diagram of deflection, maximum deflection, diagram of maximum deflection, as P is here and then move to here, 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 and it moves and goes here, as if a vehicle has joined here on the bridge. This is a bridge, and a vehicle has come here and moved slowly and went out very slowly, so that it remains static. In that case, what happens to the maximum deflection, and where does the maximum deflection occur? It will not occur at the same point, right? Only when the load is at center, it will be at the same point at the center. When the load is here, it will be somewhere here. When the load is here, it will be somewhere here. When the load is here, it will be somewhere here. So it will move. So location of maximum deflection will move. The value for maximum deflection will also change. Can you draw these two diagrams as P enters at x equal to 0 and leaves at x equal to L? These are called influence line diagram, which are very useful for designs, but you try it once yourself. Okay, I have solved the problem here. You can go through the problem. It is solved, and also said what happens when you have the load at center. That is also has been said here. Okay, so please go through this, and yeah, always draw deflection diagram, slope profile, find the location of del max, right, as well as theta max if you need to find theta max. Okay.